Hello and welcome to our lesson on statistics and what we call sampling. Before we get started here, and this is really going to be just a vocab lesson today, so that's kind of good news if you're not so much of a math person. But I want to talk about some connections and maybe distinguishing factors between statistics and the module that we just finished on probability. So for example, if I said that someone went up to bat 4 times in a baseball game and they got one hit, and they got 1 out of 4, or they went 1 for 4 that day in their at bats, is that a statistic, or could we say they have a 1 in 4 chance of hitting or getting a hit in an at bat as a probability? I'm giving you time to think. Yeah, so it sounds sort of the same, right? The difference is, and what is it really? Well, the 1 out of 4 hits is a statistic, right? And you've heard that before. You know, what are this guy's stats in the game? What are his stats for free throw shooting or athletes, right? We see this in sports all the time. Statistics are more closely related to empirical probabilities. So theoretical probabilities, like when you roll a die, a 6-sided die, you have in theory a 1 in 6 chance of landing on a 1 or a 2 or a 3 or 4 or 5 or 6. In theory, those things are equally likely to happen because when you actually perform the experiment, remember the law of large numbers, a whole bunch of times, we get fractions that are going to be closer and closer to that 1/6. So the statistics that we look at, or the probabilities that we calculate, are going to be based off statistics that were actually calculated first. Okay, so probabilities could be based off of statistics. That's one way to distinguish them. Another thing we can use to distinguish between the two is when we calculate a probability, let's say, again, of rolling a 2 on a 6-sided die. Well, we know all the outcomes when we roll the 6-sided die. We know that we could either roll a 1, 2, 3, 4, 5, or a 6. Or if I wanted to calculate the probability of picking some certain card out of a deck, I know all the outcomes because I know all 52 cards in a deck. When I need to calculate statistics, it might not be the case that we know all of the outcomes, right? Let's say you were looking for information about, I don't know, people's favorite color, okay? When people go to tell you what their favorite color is, do you know all of the options? Do you know all the different things that person could say? Right? There's probably colors out there that we haven't even heard of, okay? So when we don't necessarily know all of the options, we would have to perform some kind of experiment or some kind of observational study or some kind of a survey to collect the information, and then from that information, we could make a prediction about what the probability of a certain outcome would be, okay? So hopefully that helps distinguish the two a little bit. So statistics. In statistics, you're trying to gather and analyze and make inferences. And inferences is a fancy word for predictions. So you're trying to make inferences or predictions from data. And in statistics, there are 3 typical ways in which that data is collected. You can collect data from a survey. You can collect data from an experiment. Or you can collect data from an observational study. These are the 3 ways in which data is typically collected. Okay? And even once the data is collected, there are 2 branches of people that are going to deal with this data. So we have descriptive statisticians, or we have a descriptive branch of statistics. And in this branch of statistics, the statisticians, the people working in this branch, they're really more concerned with how is the data collected, how can we organize the data, what kind of analysis can we do, what kind of crunching of the numbers can we do with the data. So they're really concerned with the data. And then you have the inferential statistics branch. So the statisticians in this branch are going to be more concerned with, once the data has been collected and organized and numbers have been crunched, what kind of generalizations or inferences or predictions can I make based off of that data? Okay. Now there are a couple key terms in statistics. So again, it's not necessarily going to be the case that we know all of the outcomes in a survey or an experiment or an observational, oops, forgot the word study up here. So for example, again, if I wanted to know people's favorite color, okay? If I really wanted to know people's favorite color, the word people's pretty broad. Like, do I want to know what everyone in the entire world's favorite color is? I mean, maybe I do, but is it going to be possible for me to ask every single person in the world? No. So instead of asking everyone, it's which everyone would be the population, so the entire population of the globe, right? Maybe I just pick a sample of people and use the results in that sample, in that smaller group, to try to make guesses about what the entire population would be. So instead of asking, the whole world because it's not possible, maybe I just ask as many people I can in the Phoenix area, whatever, okay? Now maybe that's not realistic, like who cares about people's favorite colors? I'm just trying to throw out a concept, okay? So some key terms in statistics. A population is going to be the name for the all of the people or the entire group of people that we're interested in studying. So it consists of all items or people of interest. So whatever our topic is that we're trying to collect statistics on, everyone that's involved in that topic would be referred to as the population. But if we cannot survey or experiment or observationally study the entire population, then we might just take a sample. We take a small portion of people of interest and focus on them instead. So a sample includes some of the items of interest. Okay. Now, all this data can be collected from a population or from a sample in that population, and the data could be collected, organized. We can crunch numbers on the data, and we'll talk about ways to do that in some future topics. And then you can have the inferential statisticians who say, hey, based on these numbers, here's what we predict. But there's always the chance that it's wrong, right? You could make a prediction. So you asked 50 people what their favorite color was, and 49 out of 50 said blue. So those are pretty strong results that say blue is a pretty popular color, right? So maybe you go to ask another person what their favorite color is, and your prediction might be blue. Is that guaranteed? Well, no, because there's tons of other colors, right? So when a statistician is making an inference or drawing a conclusion from a sample, there's always the chance that the prediction is wrong. Because it is just a prediction after all. Okay, so what's the point of all this? Well, because the predictions could be pretty accurate, and sometimes it's necessary to try to make predictions depending on your situation, and pollsters do this all the time, but there's just no guarantee that the information is going to lead to the results that they predict, okay? So just so we can wrap our brains around those couple of keywords real quick. Let's say there's a MAT 141 class at GCC, and there are 26 students in that class, and the professor says, surveys the 20 girls in class about their favorite color. The class of 26 students, the whole class of 26 students in this case would represent the population. If I want to know about the favorite color of the students in my class, the students in my class would be the population. But I didn't ask all the students because apparently I was only concerned with the favorite color of the 20 girls in the class. So the 20 girls represented the sample that I decided to survey. And so 12 of the girls said that pink was their favorite color. And so another student says, well, pink is girls' favorite color. Okay, so just because 12 of the girls in my class said pink was their favorite color, again, that doesn't necessarily mean that pink is every girl's favorite color. Okay, so population's everyone, a sample is part of the population, and you use your information to try to make predictions doesn't necessarily mean that it's right. All right, so now there are three, again, typical ways that information could be collected, that statistical data is collected. One of the first ways we're going to talk about are surveys. Okay, we can survey people to collect information. So surveys, I just want to highlight there are three ways. It's one of three ways to collect data. And even within the surveys, there are different ways that data can be collected. So different types of surveys we could use to collect data. Like I could randomly, survey people. I could pick all people in a certain area. Maybe I'm standing at the entrance to the mall and I ask like every fifth person that walks in. Maybe I'm in my classroom and I only ask the girls, right? There are lots of different ways that we could collect information from a survey. But there are, 5, 6 typical ways that are in the statistics world acceptable ways to get information that hopefully doesn't create too much bias. So data can be collected or by questioning or surveying a sample or an entire population, depending on how small it is. And again, lots of ways to do this. One way is to try to collect a random sample. And actually, random could be in conjunction with some of the others that we're going to talk about. But if you're in a random sample, you have a random sample occurs in a way such that every time an item is selected, it's got an equal chance of being selected. Sort of like when you roll the 6-sided die, right? The 1, 2, 3, 4, 5, and 6 all have an equally likely chance of coming up. If you're randomly selecting someone for a survey, then anyone in the group that you're selecting had an equal chance of being selected. So if I was going to survey the students in my class, there were 26 students, and I didn't decide that I wanted to only survey the girls, I was just randomly choosing people. Well, if you're all sitting in front of me and your names are all in a hat and I'm randomly choosing them, then every one of those names in the hat had an equally likely chance of being selected. So I could just randomly choose, okay? Now, if we have a sample that's obtained by drawing every nth item on a list, like standing in front of the mall and I'm surveying every fifth person that walks through the doors, or I want a sample of people in my class, and so I sample the first student sitting in each row, or something like that. So it's every second, or every third, or every fifth, or maybe you've seen this, or had to sit in one of these lines where they do these checkpoints on the freeway, right? And they decide to randomly stop every fifth car on the freeway for an inspection. Kind of sucks to be in that line, but that's a systematic survey. So a systematic is when you are taking every nth item. Sometimes you have a sample that's taken based on a location or an area. So if it's based on location or area or geography, then we're going to call that a cluster survey. Okay. Sometimes, so a cluster survey, like if I want to know again about people's favorite color, let's say across the United States, I can't possibly survey all the people in the United States. So maybe I just focus on the ones in Arizona because I'm in Arizona. Okay. So a cluster sample is based on geography. Now, sometimes you have sampling that's involving dividing a population by characteristics that they have in common, stratifying factors like maybe I survey girls, maybe I survey, guys over the age of 18, maybe I survey, I don't know, whatever stratifying factor, like third graders, or I pick a different grade level. If there's something that the group has in common, some stratifying factor they have in common, then what we're taking is a stratified sample, using a stratified survey. Now, the next one is one that could create some bias, but sometimes it's just necessary to take a convenience sample. Convenience sample because maybe it's too hard to sample, again, everyone that's in your population. You take people that are convenient. So when I said maybe I'm going to survey the people in Arizona because they're closest to me, although that's based on geography, I could also argue that it's convenient for me to sample the people that are in Arizona. All right, and then the last one would be self-selected. In a self-selected sample, people are choosing to participate in the survey. So maybe I'm sitting, I don't know if you've ever been in the mall and you walk by these people and like, do you have time for a quick survey? And people say yes or people say no, right? Or some people keep walking like they never heard them. Those people that are saying yes and decide to stop, they are choosing to participate in the survey. So that would be a self-selected sample that group is going to be collecting. Okay? So let's get a few examples and see if we can distinguish. So you have a raffle ticket that's drawn by a blindfolded person at a festival to win a grand prize. Technically, picking a random name out of a hat would be like me picking a random student out of the group of students. That's completely random. Okay. Or students at an elementary school are classified according to grade level, and then a random sample of 3 students from each grade level is chosen to represent the class. So I mentioned this earlier, but random could be involved in most of these, and actually it should be involved in most of these. But along with the random sample of 3 students, it says they're classified by their present grade level. So we've got them grouped into grade levels. That's a stratifying factor, and then we're randomly choosing 3 from each grade level. So that's going to be a stratified sample, because we're taking these people based off something they have in common, which in this case is grade level. Every 6 car on the highway stop for a vehicle inspection. I mentioned that one a few minutes ago. That's a systematic. They are systematically stopping cars on the freeway. So every 6th, every nth is systematic. How about the first 20 people entering a water park are asked if they're wearing sunscreen? I would say that's pretty convenient, right? If you wanted to know about how many people are wearing sunscreen, it'd be pretty convenient for you to ask the people that are entering a water park if they're wearing the sunscreen, and I think you might get biased results there because you're probably more likely to be wearing sunscreen walking into a water park than if you weren't. So this is going to be a convenience one, and this is again where you might get biased results, so results that lean a particular way. Okay. How about number 5? It says voters are classified based on their polling location, and then a random sample of 4 polling locations are selected. All voters from the precinct are included in the sample. So again, you've got random here, but we have voters classified based on their polling location. So if it's based off location, we're going to call this a cluster sample. So this is a cluster survey, but it creates a cluster sample of people. Okay? And then lastly, it says a group of people walking through the mall decide to stop and participate in the survey. They are choosing to stop and participate, so this would be self-selected. Okay, so those are different ways where we could survey to collect statistical data, and survey is just one way to collect statistical data. A second way is through an experiment. So in an experiment, sometimes an experiment is performed in place of a survey. Now, why would we want to maybe experiment versus survey? What kind of situation would an experiment be more appropriate than just a survey? I'm thinking about maybe anything medical related. Okay, so let's say you're a pharmaceutical company and you've just created a new allergy pill, okay, and a new allergy medication. Do you want to survey people to decide how well you think your allergy medication is working? Probably not, right? You're going to collect better, more viable statistical data by performing an experiment. So maybe you take some thousands of let's say 10,000 people that all suffer from the same allergy. You give half of them the new medication and you leave half of them without the new medication, with no medication at all, and you compare how they react or what the results are. So you have an experiment, could be definitely more appropriate in a situation than a survey. And in your statistical experiment, there are typically 2 groups. You have what we call a control group, and you have a treatment group. And your control group represents the people that receive. You have a control group. Sorry, my eye was itching. The control group is a group that receives no experimental influence. They are considered the baseline. Okay? So again, if you had 10,000 people for your new allergy medication, 5,000 of them are not going to receive the medication. Okay? These are your baseline. Anything so the other 5 people that are getting the medication, what happens to them gets compared to those that didn't. So we can see that the 5,000 people that got the medication, they weren't nearly as nasally or congested or sneezing as much as the other 5,000 who didn't get the medication, just for example. So you've got the control group, no experimental influence. They're part of it part of the experiment just to create baseline data, and then you have the treatment group. Those would be the ones that do receive experimental influence, and those would be like the 5,000 that do get the new allergy medication, and the effects on the treatment group are compared to the control group. Okay, so as a simple example of a type of experiment, let's say there's a group of 16 identically produced Honda Civics that are selected for an experiment. Now, 8 of the Civics are driven 100 miles a day for 30 days on regular gasoline, and the remaining 8 Civics are driven the same 100 miles a day for 30 days but on premium gasoline. At the end of the 30 days, the gas mileage and miles per gallon for each of the cars will be calculated. So this is an experiment on these Honda Civics really to compare the gas mileage on regular gasoline versus premium gasoline. So in this case, the 8 Civics that are on regular gasoline, they're going to be considered the control group because regular gasoline is what most cars run on in the first place. So what's the normal gas mileage for these 8 Honda Civics? We're going to find out in that control group. And now you put the 8 Civics on premium gasoline, so you're treating them. That's the treatment group. You're treating them with an upgraded gasoline, and you're trying to decide, does it affect the gas mileage at all? Does it make the gas mileage increase? Does it stay the same? Does it decrease? What happens? Now, I don't know that this is really a great experiment because there's only 16 cars in the group, but in any case, you've got your control group and treatment group, and you have an understanding of where an experiment could be used. Okay? Now, observational studies, they have a place in statistical gathering of information as well. So the observational study, that's the third way that we could collect data. So in this case, data is collected by watching or observing. Okay, you're just watching. Now, can you think of a scenario where this would be more appropriate? Well, I think about this. This happens in education all the time. So I put an example on your paper here. There's 600 students that are being taught MAT 103. It's a new class. It's got a new curriculum. And their learning process is being monitored over the course of the semester. And their test scores and growth are being collected and recorded by the professor. This is an observational study of this new curriculum. Okay? You don't want to experiment. You don't want to take your 600 students in MAT 103, put 300 of them in one curriculum that's experimental, and then put them on the other 300 on another. It's like you're not going to experiment on curriculum, okay? And you're not going to survey the 600 students like, hey, what do you think about the curriculum in this class? Because you're going to get crazy results in something like that. Where in this case, just observing the results is going to be good. As a teacher, and this is our profession, so we know if the curriculum is working, if it's getting our students to master the concepts that we know are required for the course, then we're going to be able to verify if the curriculum is a good curriculum just based off those results. So sometimes an observational study is more appropriate than an experiment or just a survey. Okay? Now again, we got to be careful because no matter which way the statistical information is gathered, it could be organized in such a way, and then predictions and inferences and generalizations can be made in such a way that you're misled. So we have to be careful because statistical information can be used to mislead you. And we're going to talk more in this module about once the data is collected, how can we organize it, and how can we crunch the numbers, and then how do we make some predictions. We're going to talk about those things, but just to give you a little insight on ways that you could be misled, I want to show you a few things, a few graphs that I pulled from the internet just so you could see. Let's see if I can find these here. Look at this, millions of videos I have to make. Oh, here we go. Okay, so I pulled some graphs from the internet, and again, we're going to talk more about this in depth later, but just kind of for fun. So this graph shows the thoughts when a car alarm goes off. So when a car alarm goes off, according to this graph, there's a huge section of green here that says people are thinking, man, that's annoying, turn it off. And then you got this one little sliver of red here where someone's car is actually being stolen. That's no good. So when a car alarm goes off, what do you think about this graph? Like, is this accurate? Or do you think most people are thinking that that's annoying, they should turn the alarm off? Do you think it's possible that there's just a small portion of people that are actually having their car stolen? Maybe that's true, and that's what the graph is trying to tell us, but are there some issues with this graph? Well, of course there are issues, because aren't there other thoughts that could occur when a car alarm goes off? I would hope. If I hear a car alarm go off in my neighborhood, my first thought is that my car or is that a neighbor's car? Like, there are other thoughts that aren't represented in this picture. And a bigger issue is this graph is supposed to encompass 100% of people in a survey. Well, we don't know how many people were surveyed here. We don't know what the population was or the sample. I don't know if this is 100% of the results, or maybe they just pictured the two that they wanted to take. Okay, so even though it's sending a message that's probably resonating with a lot of people, this graph is misleading. Okay, how about this? When falling asleep feels the easiest. So apparently, from this graph, what I'm gathering is that when you're in class, it's really easy to fall asleep. When you're at work, it's still easy, but not as easy to fall asleep. And when you're in bed actually trying to sleep, boom, it's way down here. So this graph, I think what it's trying to tell me is hard to fall asleep here, harder to fall asleep here, and this is a little easier, and this would be the easiest time to fall asleep, is when you're sitting in class. Now, again, that's what the graph is trying to tell me, but you see some issues here. Well, how do you measure how easy it is to fall asleep? Like, what is this bar graph actually measuring? And when it says it's 100, it's 100. How easy it feels to fall asleep. 100 easy to fall asleep. Like, what does that 100 mean? Or what is this? I don't know. What is it, like 82-ish? What does that mean? Or this 0? It's 0 easy to fall asleep. 0 what? Like, what are the units there, and what does this mean? And how many people were surveyed? What's the population in the sample? I don't know. Lots of problems with this graph. So even though it leads you to believe something that might resonate with you, like, well, what is this graph? Okay? So issues we should be looking for and making sure we're not just taking a graph at first sight and buying what it's saying. Okay? All right, here's another one. We see stuff like this all the time. Fly Speedway Airlines save 20%. That's kind of vague. So vagueness is an issue in statements and in graphs. We just saw that in a couple. When it says save 20%, what does it mean? Does it mean 20% off your entire bill? Is it 20% off of non-sale tickets? Is it 20% off of sale tickets? Is it 20% off the luggage that you're carrying on? Is it 20% off the soda that you might have while you're sitting on the plane? I don't know. So we have to be really careful with advertisements and ambiguity, right? Vague statements that could be interpreted multiple ways. All right, how about this one? Oh, here's another graph one. At first glance, right, we've got stock A, we've got stock B, and it looks like the graphs are showing the price of the stock over a certain number of months. Now, at first glance, looking at these pictures, which stock looks like it's performing better? Well, at first glance, it looks like stock B is increasing a little faster than stock A. So just by looking at this picture, I'd be like, oh, I gotta go with stock B. If I'm a stock investor, right, I gotta choose B. It's increasing faster. But if you look a little more closely, let's look at the data points here. So this first graph says in January we're about 25. And then over here, if we go to January, look at still 25. February, we're up a little bit. I don't know, maybe that's 26. And then February, oh yeah, it's like 26, 27. These are actually the same exact graphs. So why do they look different? Why do they look different? Maybe you're seeing that in this particular graph, the axis is broken. So nothing's happening here. Let me just cut that piece of the graph off so I can stretch it out. Well, when you break an axis like that, it's distorting the picture, and you could see it, that this graph looks much flatter than this one does, and that's because of the break in the axis. So you have to be careful when you're looking at graphs. If the axis is broken, it could be distorting the picture. It could be making it look like it's doing something that's not really happening. All right, and that could be used like this to mislead you into thinking that stock B is better, but really these things are doing the same. Okay, how about this guy, the perception of a minute? So apparently when you're having fun, a minute feels like a half a minute. When you're doing nothing, a minute feels like a minute and a half. When you're being tortured, a minute feels like 4 minutes. And then when you're waiting for something to load on a computer, that your minute feels like 9 minutes. Again, maybe something you relate to. But what's the issue here? Okay, what's one issue here? Well, how do you measure your perception of a minute? So, man, that minute felt like forever. That minute felt like 4 minutes. How do you actually measure that? It isn't something you can measure. You can't measure how long you perceive a minute to be. So, again, this graph clearly resonates with people, but we don't know how many people were surveyed. We don't know how these measurements were made. This is like craziness, okay? All right, let me show you another one. I think this is, yeah, this will be the last one. Usage of a home gym, okay? So the week you bought your home gym, the week you bought it, you used it 7 days. 1 week after, you only used it 5 days. The week after that, you only used it 3 days. And then the month after that, boom, not using your home gym. Okay, so maybe this is accurate, and I don't think there's any issue with the measurements here, but I do see some issues, like how many people were in this population, how many people were sampled from the population? Does this graph represent what happened to one person, or is this results from a whole bunch of different people? That'd be good information to know, right? And then what about, like, who would make a graph like this? Like, who would do this? What kind of person would put out a graph like this in the first place? Like, why was I able to even go online and find this? It's ridiculous, right? Because I have no life. No, no. Why was I able to go online and find this? I would imagine that if you, let's say, owned your own gym, right? If you owned a little small, like, mom and pop gym, and you want people to come to your gym, you might show them a graph like this, because someone might come in and be like, okay, I don't know if I want to spend $60 a month coming to your gym when I can just put that money toward my own gym that could be at my own house and that isn't going to get shut down by COVID, right? Well, they're going to say, well, why would you do that? You can put your $60 a month or whatever it is into your own home gym, but after a month, you're not even going to be using it. Where if you pay us the $60 a month, when you decide you don't want to come anymore and you want to stop using the gym, you just stop paying. So you can see how graphs can be misleading on their own, but there are particular groups of people that are going to try to purposely mislead you with graphs. So this graph might be completely 100% truth for, I don't know, one person. What if this represents one person? Okay? This graph could be 100% legitimate for that one person. But does that mean it should be the basis for you making a decision about your home gym? Probably not. Okay? So you really have to be careful in statistics with vague statements, graphs that are misleading, who's trying to mislead you, right? You really should be asking questions about information before you make decisions. And then as we move through the module, we're going to talk about different ways to make these kinds of pictures ourselves from data and analyze and crunch the numbers a little more. And hopefully by the end of the module, we'll feel a little bit better about all of this. Okay? That's it for this time. Hopefully the practice isn't too much of an issue for you, but if you run